Welcome. This is Mr. Collier, and I just want to sit down and have a chance to review some of the information that we already know. So most of this will not be new. A little bit the velocity versus time graphs will be new, but this is a nice way to get it into our notes that we can learn and study from. So first of all, we have to sort of point out that the acceleration we're talking about here is for uniform acceleration. So sometimes in class, a few of the students have talked about a constant rate of change. And that's what we're really talking about. Like the graph we did in our earlier lesson, the acceleration in that lesson was 10 centimeters per second every second. So it got 10 centimeters a second faster for every second. And so that's what we're going to talk about on this page. The acceleration isn't changing, although the velocity certainly is. So let's look at the first one here. We're going to fill this in. And I would invite you to review this and then fill it in yourself. So we're going to do two position versus time graphs, one with a smaller incline and one with a greater incline. And we might call this one, from our lab, the one where the wheel-on ramp was raised with 2 books, and maybe this one is raised with 3 books. The numbers aren't important, it's just that this has a steeper incline than this one. So these are position versus time graphs. They're just sketches, but let's go ahead and label the axes. And on both of these, position and time. And because this is for acceleration, when we look at the position versus time graph for acceleration, it's going to start out slower, and as time goes on, it's going to get faster and faster. And that's what we see here. On this graph, if we look at the slope in this part of the graph versus this part of the graph, here the slope is less, here the slope is more, meaning slower here and faster there. But let's compare it to a book with a greater, or a wheel or an object with a greater incline. If we look at that position versus time graph, because it's a greater incline, it's going to speed up faster. So if we look at the difference between the first graph with 2 books and the second graph that perhaps had 3 books raising the ramp, we can see that this one got faster. So as we look, the slope increased at a greater rate. So this one is a lower acceleration, this one is a higher acceleration. Now the next thing we have to talk about is something a little bit new, and this is the velocity time graph. And this is a new thing for us. We've always talked about position versus time, and now we're going to talk about velocity on the y-axis versus time on the x-axis. And I'm going to take these 2 graphs that we just did and now put them on this new kind of graph. So if we look at the graph with where the ramp was raised, for example, with 2 books, we know that because of this graph, its velocity is ever increasing. So to show that on this graph, we just have a line that's straight. And this means that as the time goes on, the velocity is increasing. It's getting faster and faster. And let's go ahead and label that as the 2 books line. And now let's compare it to the ramp that was raised with 3 books. And we can know from what we said before that wheel was getting faster at a faster rate. So we can draw that in on the velocity time graph as a steeper line, saying that as time went on, it got faster and faster at a greater rate. And let's just label that 3 books. And just to put some units here, if we were going to talk about this in the wheel-on ramp example, this velocity on this side would be in centimeters per second, and time would still be in seconds, so that if we took the slope of these lines and we divided delta y by delta x, we would have centimeters per second per second. And that would be a nice thing to remember. So let's look at it a little bit different way, something you have to know as we continue to talk about velocity time graphs, and that is there's something we have to understand. And I'm going to draw this one, this format. So velocity again is on the y-axis, time is on the x-axis. This is 0 velocity and 0 time, and this is positive velocity like we saw over here. And we know this is a regular Cartesian coordinate system, so even though we didn't draw it over here, we could still draw part of the axis coordinates to go down like that. So I just have to tell you this because this sometimes gets a little confusing for people. But on a velocity time graph, sort of the thing that we always accept and we all agree on is that this quadrant up here always means that the object is moving away from the origin. So anytime we see a graph line up in here, it means it was moving away from the origin, and down here is towards the origin. And as we move forward using velocity time graphs, this becomes very important. And honestly, if you just remember this, it'll help interpreting velocity time graphs a lot. You'll be very thankful for that. So let's move on to the more of this page. And what it says over here is, let's write down the equation. Let me zoom in a little bit for the position time graphs. And this should be an old familiar thing to you. And so we'll have, let's say here, that slope on a position versus time graph. We use the symbol M to represent slope. And that is, when we do a slope of a PT graph, that gives us speed or velocity. Speed or velocity. And the formula for that is slope, which is M again, the symbol we use, is the change in y divided by the change in x. In this case, the change in distance divided by the change in time, and that gives us our speed or velocity. That should be very familiar to you. But now let's look at the equations for a velocity time graph. Again, so slope of a velocity time graph is equal to acceleration. And if we look back up here again, if we divide centimeters per second by seconds, when we calculate the slope, that gives us an acceleration unit. And so let's continue down here. Slope is equal to, the change in y divided by the change in x. And in a velocity time graph, that means the change in velocity divided by the change in time, and that is equal to acceleration. And let's just remind ourselves that acceleration, well, let me move it. Acceleration is a change in velocity. That's really important. We've talked about that. And velocity is speed in a given direction. So a change in velocity means we can change the speed or we can change the direction. Now, this next one we want to fill out says, what does the slope of a velocity time graph mean? And we just talked about that. Let's just write it down. Slope of a velocity time graph is acceleration. And just to remind ourselves, acceleration is an increase in speed a decrease in speed, or a change in direction. And that's really important to remember as well, especially with a nice quiz coming up. Now, we're getting near the end, and I want to sort of convert these ideas we've been talking about into motion maps. So let's go back again to talking about the ramp with 2 books holding it up, the small incline, and the ramp with 3 books holding it up, the big incline, just to remind ourselves. And let's think about what this will look like. On both the 2-book and 3-book ramps, the wheel always starts at the origin, so we're going to start here at the origin, put our dots. Always have to have a dot on a motion map. And I'm going to draw an arrow. Now, because this is acceleration, as we go, the dots are going to get further and further apart until we go off and we don't care anymore. And now with the 3-book, it also is going to start at the origin, but it's going to get faster, if I can use that informal description. And so this is what a motion map would look like for both of those position versus time graphs that we looked at the top, 2 books and 3 books. Now let's move on to the last part of this first page, and that is a generalized velocity time equation. And again, we're going to write this out. Acceleration is equal to the change in velocity over change in time, meters per second or centimeters per second. And one of the ways we can calculate that, and most of you have already done that for me, is that we can start off with speed final, subtract the initial speed, and divide that by time. And the formula I would like you to write is S sub f minus S sub I divided by t. And that's something that you should get comfortable with. All right, ladies and gentlemen, I'm all done. I hope that will help you as you move forward. You can use this lab analysis guide as a reference to help you work out questions and to remind you of what we've talked about in class. Thank you so much.